CW Leonis, a massive carbon star hidden amidst the star-filled sky, is not just a bright point in the cosmos, but a colossal physical machine with peculiar and spectacular characteristics. What has made this star a focal point in astronomical research? The scale and structure of CW Leonis, also known as IRC plus 10216, is one of the largest and brightest carbon stars ever observed by astronomers. Located approximately 650 light-years from Earth in the constellation Leo, CW Leonis stands out not only as a prominent star, but also as an ideal, natural laboratory for studying carbon stars. The star's unique appeal lies in its immense size and scale, making it a key subject of scientific investigation. With a staggering radius approximately 560 times that of the Sun, CW Leonis would extend beyond the orbit of Mars if placed in the solar system, encompassing a significant portion of our planetary system. Despite its vast size, the star's mass is relatively modest, estimated between 1.5 to 4 times the Sun's mass. This stark contrast between mass and size results in an extremely low density, making CW Leonis resemble a giant cloud rather than a compact star. Its outer layers are exceptionally thin and unstable, expanding and contracting in regular cycles, a phenomenon scientists describe as a pulsating giant star. This structural peculiarity not only makes CW Leonis unique, but also provides valuable insights into how carbon stars form and evolve. The breathing cycles of CW Leonis, where the star continuously expels matter and energy into interstellar space, are integral to this process. The ejected layers of gas contain heavy elements like carbon, oxygen, and silicon, essential building blocks for the formation of new stars and planets. These carbon-rich materials enrich the surrounding environment, playing a crucial role in sustaining life and shaping the structure of the cosmos. The juxtaposition of CW Leonis's immense size and modest mass sheds light on how gravity operates in stars nearing the end of their life cycle. With its low density and loose structure, the star's gravitational pull is insufficient to retain its outer layers, which are continuously blown into space. This process not only shapes the evolution of CW Leonis, but also offers clues about how other giant stars in the universe transition through their final stages. Scientists believe CW Leonis is nearing the phase of becoming a planetary nebula, where its outer gaseous layers are entirely expelled, leaving behind a smaller stellar core known as a white dwarf. Moreover, the light emitted by CW Leonis provides invaluable information. Using spectroscopy, scientists have analyzed this light to determine the star's chemical composition and the reactions occurring within it. Findings reveal that CW Leonis is not only a powerful light source, but also one of the most prolific carbon producers in the surrounding cosmic region. This underscores the importance of carbon stars in enriching the universe with the elements necessary for planetary systems and life. The pulsations and material ejections of CW Leonis also offer deep insights into how giant stars contribute to galactic evolution. Each breath of CW Leonis releases significant amounts of matter into interstellar space, forming clouds of gas and dust that can eventually become the birthplace of new stars and planets. This highlights the central role of carbon stars, like CW Leonis, in maintaining and regenerating life in the universe. In summary, CW Leonis is a vivid testament to the scale and power of carbon stars. With its colossal size, fragile structure, and capacity to produce heavy elements, this star illuminates the physical and chemical processes of the cosmos, while helping us better understand the formation of stars and planets. Though nearing the end of its life, CW Leonis continues to inspire and provide critical data, advancing astronomy and opening new doors to cosmic exploration. The remarkably cool surface of CW Leonis. One of CW Leonis's most striking characteristics is its surprisingly low surface temperature compared to typical stars. With a surface temperature of only about 2,300 Kelvin, approximately 2,027 degrees Celsius, CW Leonis is significantly cooler than the Sun, whose surface temperature reaches about 5,778 Kelvin. This disparity reflects the unique nature of CW Leonis, a carbon star in its final stages, nearing the depletion of its fuel. This low temperature originates from the nuclear fusion processes occurring in the star's core. As CW Leonis transitions to burning heavier elements like carbon and oxygen instead of hydrogen, the energy generated decreases significantly. Consequently, the star's outer layers expand and thin out, reducing its surface temperature. Despite its coolness, CW Leonis's enormous size, roughly 560 times the Sun's radius, allows it to shine brightly in a characteristic red hue, akin to a cosmic ember glowing faintly in the galaxy. However, its low temperature does not diminish CW Leonis' importance in astronomical research. On the contrary, this trait makes it an ideal target for studying the evolution of carbon stars. At this temperature, CW Leonis's dense atmosphere provides a perfect environment for the formation of complex molecules and cosmic dust particles. These dust particles, composed of elements like carbon, silicon, and oxygen, enrich the interstellar medium and play a crucial role in dispersing heavy elements into space, raw materials for new generations of stars and planets. These dust particles and molecules also bring another fascinating feature: the ability to emit energy in the form of infrared light. When these dust particles absorb energy from the star, they re-emit it as distinctive bands of light in the infrared spectrum. This fingerprint enables scientists to determine the chemical composition of CW Leonis's atmosphere, offering insights into how carbon stars disperse material. These findings illuminate the role of CW Leonis in enriching the interstellar environment and provide critical information about the late stages of giant stars. Additionally, CW Leonis's low temperature directly influences the type of light it emits. Instead of predominantly visible light like the Sun, CW Leonis's radiation mainly lies in the infrared spectrum. This makes the star a prime target for infrared telescopes like the Spitzer or James Webb Space Telescopes. Observations from these instruments have offered detailed views of how carbon stars operate and develop in the cosmos. The cool surface temperature also impacts CW Leonis's evolutionary trajectory. As the star continues to lose energy and matter, its outer gaseous layers will gradually be expelled into space, forming a surrounding dust shell. Eventually, CW Leonis may transform into a planetary nebula, where its outer atmosphere dissipates completely, leaving a compact stellar core, a white dwarf. This process illustrates not only the evolution of carbon stars, but also their role in recycling matter within the universe. CW Leonis is more than a fading star. It is a valuable laboratory for studying the interactions between temperature, atmosphere, and matter in the cosmos. From the formation of dust particles to the dispersion of energy through the infrared spectrum, this star provides essential data that helps us understand how carbon stars enrich the interstellar medium and influence galactic evolution. In conclusion, CW Leonis' low surface temperature is not just a unique trait, but a vital factor in unraveling the processes occurring in carbon stars. The data from CW Leonis expands our knowledge of giant stars while offering deep insights into how factors like temperature, matter, and energy shape the universe's development. Though nearing the end of its life, CW Leonis continues to make significant contributions to humanity's ongoing journey to uncover the secrets of space. Pulsation and variability in CW Leonis, or IRC plus 10216, is not a stable star, but belongs to the Mira variable class, known for their periodic brightness fluctuations. Each cycle of CW Leonis lasts several hundred days, during which its brightness can vary significantly. This variability not only underscores the unique characteristics of CW Leonis, but also reveals complex mechanisms within the star's structure and activity. The primary cause of this phenomenon lies in the expansion and contraction of the star's outer layers. When the outer shell contracts, the temperature increases, causing the star to shine more brightly. Conversely, when the layers expand, the temperature drops and the brightness dims. This breathing cycle affects not only the star's brightness, but also its size and chemical composition. With each expansion, CW Leonis ejects large amounts of gas and dust into space, forming a shell of material around the star. These breaths can be seen as the lifeblood of CW Leonis, each leaving an imprint on the interstellar medium. The expelled gas and dust contain elements like carbon, oxygen, and silicon, fundamental components for the formation of new stars and planets. This makes CW Leonis a cosmic recycling plant, continuously contributing material to the interstellar environment. The dust particles expelled also radiate strongly in the infrared spectrum, providing valuable data for scientists to analyze the star's structure and chemical composition. The variability in CW Leonis' brightness and size is not just an intriguing feature, but also holds significant implications for understanding the life cycles of giant stars. This process of expansion and contraction signals that CW Leonis is in its final stages. As the star continues to shed its outer layers through these breaths, it approaches the point of becoming a white dwarf, a hot stellar core left after most of its material has been expelled into space. This stage not only represents a transition in the star's evolution, but also enriches the interstellar medium with elements essential for the formation of new generations of stars and planets. The pulsation of CW Leonis also offers profound insights into the workings of carbon stars. During these cycles, changes in temperature and pressure in the outer layers create conditions conducive to forming complex molecules and dust particles in its atmosphere. These dust particles not only absorb and re-emit light, but also serve as fundamental building blocks for new celestial bodies. Thanks to the strong infrared emissions from this dust, scientists can gather detailed data about the chemical composition and atmospheric structure of CW Leonis, deepening our understanding of the physical processes within the star. Looking further, CW Leonis' variability highlights the crucial role of Mira variables in redistributing matter within the galaxy. As stars like CW Leonis expel material into space, they form massive clouds of gas and dust, which can become the birthplace of new stars and planets. This underscores the importance of Mira variables not only in astronomical research, but also in understanding how the universe renews and develops itself. Over the next few million years, CW Leonis will continue breathing until it expels most of its remaining material, revealing a small, hot core, a white dwarf. This phase marks the end of CW Leonis' life cycle, but also the beginning of a new cosmic journey. The layers of gas and dust left behind will drift through space, contributing to the formation of future stellar systems. In summary, CW Leonis' pulsation cycles are not only a fascinating phenomenon, but also provide extensive insights into the evolution of carbon stars and their role in enriching the universe. The breaths of CW Leonis are not merely signs of survival in its final stages, but also an inspiration for astronomical research, opening new doors to understanding how the universe operates and perpetually regenerates itself. CW Leonis. The dense atmosphere of the star containing carbon compounds and its slow cooling conditions. When observing CW Leonis, we do not merely see a dying star, but also discover a natural laboratory with a unique atmosphere where carbon and complex compounds are creating unprecedented slow cooling conditions in the universe. The unique atmosphere of CW Leonis. The atmosphere of CW Leonis, also known as IRC plus 10216, is one of the most striking features of this carbon star, drawing special attention from the scientific community. With its immense carbon content, CW Leonis's atmosphere contains a range of complex chemical compounds that few other stars in the universe can rival. Compounds such as acetylene, C2H2, and cyanogen, CN, two prominent molecules in its atmospheric composition, have been detected through infrared observations, where the starlight interacts with these molecules, leaving distinct signatures in the spectrum. CW Leonis's atmosphere has been likened to a dense carbon veil enveloping the star, dimming the light emitted from its surface. This atmospheric layer not only serves a protective function, but also contributes to the star's distinctive appearance. Acetylene, a byproduct of chemical reactions in the atmosphere, is the primary reason for the bright orange-red hue CW Leonis displays when observed from Earth. This feature not only enhances the star's unique beauty, but also provides crucial insights into the chemical processes occurring within this extraordinarily different environment. Cyanogen, a highly toxic and rare compound, is another significant component of the atmosphere, underscoring the chemical richness of CW Leonis. Remarkably, the atmospheric composition of CW Leonis is not random, but rather a product of the star's late evolutionary stages. As CW Leonis breathes, it ejects layers of material from its surface, including carbon and other heavy elements, into the interstellar medium. During this process, under high temperature and low pressure conditions, simple molecules combine to form complex compounds. This mechanism is vital not only for the evolution of CW Leonis, but also for the universe, where fundamental elements are recycled and dispersed to form new stars and planets. CW Leonis' atmosphere also serves as a valuable natural laboratory for studying how complex organic compounds form in the universe. Observations from infrared telescopes, such as Spitzer and James Webb, have provided detailed data on compounds like acetylene and cyanogen, enabling scientists to better understand the chemical reactions occurring in this atmospheric environment. The presence of these compounds suggests that the extreme conditions of carbon stars may foster the development of organic molecules, an essential component for life. Beyond offering crucial data on carbon stars, CW Leonis's unique atmospheric composition raises profound questions about chemical evolution in the universe. The elements and compounds from CW Leonis's atmosphere not only enrich the interstellar medium, but could also be the precursors to the formation of planetary systems and, ultimately, life. This is particularly significant as scientists explore how similar chemical and environmental conditions might exist in other stellar systems, especially those with Earth-like planets. Furthermore, CW Leonis's atmosphere provides insights into how carbon stars interact with their surroundings. Carbon compounds, when expelled into space, form interstellar clouds of gas and dust, which may become the birthplace of new stars. This emphasizes CW Leonis' role as a cosmic recycling factory, where fundamental elements are supplied to future generations of stars and planets. The star's chemically rich and unique composition not only illustrates the diversity of carbon stars, but also sheds light on their role in sustaining and regenerating the building blocks of life. In summary, CW Leonis's unique atmosphere is not just an astronomical curiosity, but also a key to understanding the universe. With its complex chemical compounds and vital role in redistributing matter, CW Leonis is a vivid example of how carbon stars enrich the interstellar medium and drive galactic evolution. The study of this atmosphere continues to open new opportunities to explore how organic compounds and heavy elements form, and their role in the universe's development. CW Leonis is not just a remarkable carbon star, but also a gateway to unraveling the greater mysteries of the cosmos. The formation of dust and slow cooling effects. One of CW Leonis's notable characteristics is its ability to produce dust particles from its carbon-rich atmosphere. Carbon, when combined with other elements under specific temperature and pressure conditions, forms small dust particles. These particles gradually accumulate, forming dense layers of dust surrounding the star, playing a critical role not only in the atmospheric structure, but also in controlling CW Leonis's energy emission and absorption. The dust formation process is a direct result of the chemical evolution within the carbon star's atmosphere. As CW Leonis expels material during its pulsation cycles, carbon and other elements ejected into space interact and coalesce into small dust particles. These particles continually grow in size and density, creating a massive shield around the star. This dust layer absorbs much of the radiant energy from the star's surface and then re-emits it as infrared light, helping CW Leonis maintain stability longer than similar stars. The slow cooling effect provided by the dust layer is a crucial factor in extending CW Leonis's lifespan. By preventing a significant portion of thermal energy from escaping, the dust layer creates a natural insulating environment, reducing the star's cooling rate. This explains why CW Leonis, despite having a low surface temperature of about 2,300 Kelvin, can remain stable and continue to exist for an extended period. This effect not only keeps the star in equilibrium, but also slows its decline, allowing CW Leonis to breathe and eject material through multiple cycles. Beyond influencing CW Leonis itself, the dust formation and slow cooling processes have broader implications for the evolution of carbon stars in general. The dust produced by CW Leonis not only surrounds the star, but is also dispersed into the interstellar medium, contributing to the formation of massive nebulae. These nebulae serve as the birthplaces of new stars and planets, functioning as a factory that recycles material within the galaxy. This underscores the central role of carbon stars like CW Leonis in providing the raw materials for the creation of future celestial bodies. The dust layer from CW Leonis not only enriches the interstellar medium with carbon, but also carries other heavy elements like oxygen and silicon, essential components for forming solid celestial bodies. These dust particles can coalesce in space, becoming the fundamental building blocks for planets or even new stars. This is why carbon stars like CW Leonis are considered the architects of the universe, continuously recycling and distributing elements necessary for life and galactic evolution. The dust formation and slow cooling processes of CW Leonis also offer new perspectives on how carbon stars interact with their environment. The dust layer is not merely a byproduct of chemical reactions, but an integral part of how the star maintains equilibrium. Infrared observations from modern telescopes like James Webb have provided detailed data, helping scientists understand the structure and composition of this dust. These findings not only expand our knowledge of CW Leonis, but also offer clues about how other carbon stars in the universe operate. In conclusion, the dust formation and slow cooling effects of CW Leonis are not just fascinating astronomical phenomena, but also critical for understanding the evolution of carbon stars. The dust layer not only helps CW Leonis maintain stability, but also plays a significant role in redistributing matter within the galaxy. The tiny dust particles from CW Leonis carry the story of the universe's formation and evolution, inspiring scientists to delve deeper into the secrets of the vast cosmos. The role of CW Leonis as a matter launcher. CW Leonis, or IRC plus 10,216, is not only renowned for its carbon-rich atmosphere, but also stands out as a powerful matter launcher in the universe. With each pulsation cycle, the star continuously expels massive clouds of carbon-rich gas and dust, forming a thick shell around it. Observations from infrared telescopes like Spitzer and James Webb have revealed that these clouds can extend thousands of light-years away, far surpassing the star's size. This makes CW Leonis a cosmic recycling hub, where matter is perpetually regenerated and redistributed. The material clouds ejected by CW Leonis not only enrich the interstellar medium with elements like carbon, oxygen, and silicon, but also contain complex compounds, the building blocks for new stars and planets. Carbon, one of the most vital elements for life, is released by CW Leonis in vast quantities, serving as a construction material for future celestial bodies. When these particles merge with other interstellar clouds, they create the conditions for the birth of subsequent generations of stars and planets, directly contributing to the cosmic matter cycle. This process of matter ejection is not only a fascinating physical phenomenon, but also crucial for understanding the role of carbon stars in galactic evolution. As CW Leonis expels material, its gas and dust layers are propelled outward by radiation pressure and powerful stellar pulses. These streams of matter not only form visually stunning structures in space, but also carry heavy elements forged in the star's core. This demonstrates that CW Leonis, while nearing the end of its life, actively contributes to the regeneration of matter within the universe. Beyond enriching the interstellar medium, the dust clouds from CW Leonis offer a unique opportunity to study the interaction between carbon stars and their environments. Infrared observations show that these clouds are not uniform in composition or structure, suggesting that the ejection process may be influenced by factors such as stellar cycles, radiation pressure, and interactions with other interstellar clouds. These are valuable clues that help scientists better understand the mechanisms of carbon stars and their role in maintaining the galactic matter cycle. One particularly intriguing aspect of CW Leonis's matter ejection is its contribution to shaping nebulae in the universe. As the dust and gas clouds drift into space, they form intricate and beautiful structures, such as rings or filaments within nebulae. These structures are not merely remnants of a dying star, but also the cradle for new stars and planets. This illustrates that in the universe, the death of one star is not an end, but the beginning of a new life cycle. Furthermore, the material clouds from CW Leonis vividly demonstrate that the universe operates as a cyclic system, where the death of one star can bring life to others. This process highlights CW Leonis's role as a recycling plant in the galaxy. The heavy elements it ejects not only enrich the interstellar medium, but also serve as nuclei for forming new celestial bodies. This confirms that the existence and evolution of carbon stars are not only vital to themselves, but also have far-reaching impacts on the structure and development of the universe. In summary, CW Leonis matter ejection process is not just an impressive physical phenomenon, but also holds great significance in understanding the galactic matter cycle. With each dust and gas cloud expelled, CW Leonis not only enriches the interstellar medium, but also acts as a creator, paving the way for the formation of new stars and planets. Research on CW Leonis not only unravels the mysteries of carbon stars, but also sheds light on their role in the universe's continuous evolution. CW Leonis, though in its final stages, continues to contribute to the life and rebirth of the universe, proving that the death of a star is not the end but the beginning of what comes next. The potential threat from stars, like CW Leonis, to surrounding planets. Although CW Leonis is a massive physical engine radiating brilliantly across the cosmos, it also poses a potential threat to nearby planets. From destructive radiation to orbital disruptions, this star not only marks the end of its own existence, but also has the power to shape or destroy the worlds around it. The destructive radiation of CW Leonis, or IRC plus 10216, is not just a massive carbon star with a dense atmosphere, but also a powerful source of radiation, particularly infrared and ultraviolet (UV) radiation. These types of radiation not only affect the star itself, but also have profound impacts on the surrounding environment, especially nearby planets. The radiation emitted by CW Leonis can alter the climate of nearby planets and completely destroy habitable conditions, turning them into barren, lifeless lands. Infrared radiation from CW Leonis plays a critical role in interacting with dust particles and carbon gases in space. When this radiation reaches nearby planets, especially those with atmospheres, it triggers a strong greenhouse effect. Dust particles and carbon gases absorb the radiation, re-emitting it as heat, significantly raising the surface temperatures of these planets. This process not only causes extreme temperature increases, but also alters the climate systems of the planets. Over time, high temperatures can evaporate water and atmospheric gases, leading to a severe reduction or even total loss of their atmospheres. The effects of ultraviolet radiation from CW Leonis are even more alarming. This type of radiation has a high destructive potential, strong enough to break chemical bonds in the atmospheric molecules of nearby planets. When molecules like water, H2O, or methane, CH4, are broken apart, the atmospheric composition changes rapidly and unpredictably. Such changes can weaken or entirely destroy a planet's natural protective layer, exposing its surface to direct cosmic radiation. As a result, these planets quickly become lifeless wastelands, incapable of supporting life as we know it. Furthermore, dust particles and carbon gases emitted by CW Leonis intensify heat absorption, amplifying the destructive effects of radiation. These dust particles act as energy-absorbing surfaces, retaining heat in the interstellar environment and transferring it to nearby planets. Combined with the intense radiation from the star, this creates an endless feedback loop where temperatures continue to rise, exacerbating the radiation's impact. Consequently, the surrounding planets not only suffer from rising temperatures, but also face atmospheric pressure loss, creating harsh, nearly uninhabitable environments. Additionally, CW Leonis's radiation affects the structure and composition of the atmospheres of nearby planets. The destruction of chemical bonds and the loss of essential atmospheric molecules like ozone weaken the protective capabilities of these atmospheres, making planets more vulnerable to external factors. Once the atmosphere is stripped away or severely diminished, the planetary surface is exposed to direct radiation and high-energy particles from the star, transforming them into desolate landscapes incapable of sustaining life. These phenomena not only impact nearby planets, but also serve as a stark reminder of the destructive power of carbon stars like CW Leonis. In the context of astronomy, CW Leonis vividly illustrates how a carbon star can reshape and completely transform its surrounding environment. Studies of radiation from CW Leonis provide valuable insights into how carbon stars interact with nearby planets, opening new avenues for research on the survivability and evolution of planetary systems in harsh environments. In summary, the radiation from CW Leonis is not only a defining feature of the star, but also profoundly affects nearby planets. Infrared and ultraviolet radiation not only alter climates, but also destroy atmospheric structure and composition, turning planets into lifeless zones. Simultaneously, dust and carbon gases emitted by CW Leonis exacerbate the destructive effects, highlighting the role of carbon stars in shaping the interstellar environment. These impacts underscore the immense power of CW Leonis, while offering valuable lessons on how cosmic forces influence the development and evolution of planetary systems. Orbital disruption by CW Leonis. As CW Leonis approaches the final stages of its life, it will undergo dramatic transformations, including the ejection of its outer layers and collapse into a white dwarf. This process not only reshapes the star's structure, but also profoundly affects the orbits of surrounding planets, disrupting the gravitational balance within the stellar system. When CW Leonis expels massive amounts of dust and carbon gas, these materials can form an enormous gaseous shell around the star. This shell not only enriches the interstellar medium, but also exerts gravitational drag on nearby planets. Planets within the vicinity of CW Leonis will experience significant orbital changes. Some may be pulled into unstable orbits, facing the risk of destruction or being engulfed by the gaseous shell. Conversely, other planets may be pushed away from the stellar system due to gravitational imbalances, causing them to drift into interstellar space as rogue planets. This disruption affects not only the positions of planets, but also their structures. Planets engulfed by the dust and gas-rich shell of CW Leonis may undergo accretion, where material accumulates on their surfaces, altering their chemical composition and atmosphere. This can lead to the formation of new features or even a complete restructuring of the planet. However, this accretion process comes with significant threats, including high temperatures and strong pressures from the surrounding materials, rendering these planets even more inhospitable. For planets ejected from the stellar system, their journey as rogue planets presents different challenges. Without a stable energy source from a parent star, these planets will become cold and dark, losing all conditions necessary for supporting life. Nevertheless, rogue planets also raise intriguing questions about the potential for life to develop or adapt in such extreme conditions. Could these planets become potential habitats if adopted by another star system? Orbital disruption not only demonstrates the dominant power of gravitational forces, but also highlights the destructive potential of a star like CW Leonis on its surrounding environment. As the star loses much of its mass during material ejection, its gravitational pull weakens significantly, completely altering the dynamics of the stellar system. Planets that were once stable in their orbits are now caught in a dangerous interplay of gravitational forces and ejected materials from CW Leonis. These changes are not merely a manifestation of astronomical collapse, but also raise critical questions about the adaptability and survival of remaining planets within a dying star system. Can they maintain stability in the new environment, or will they face complete destruction? These questions are not only theoretically significant, but also practically valuable for understanding the life cycles of stellar systems and planets. Furthermore, orbital disruption during CW Leonis's final stages helps scientists better understand how carbon stars influence the broader cosmic environment. The gas and dust ejected from the star not only impact nearby planets, but also spread into the interstellar medium, forming new structures such as nebulae. These nebulae can become the birthplace of new stars and planets, illustrating the ongoing cycle of matter in the universe. In conclusion, the orbital disruption caused by CW Leonis is not only an impressive astronomical phenomenon, but also provides vital insights into the dynamics of stellar systems. From pulling planets into unstable orbits to ejecting them into interstellar space, C.W. Leonis demonstrates that the death of a star affects not only itself, but also shapes the destiny of surrounding celestial bodies. This process is not merely the end of a star, but also the beginning of a new cycle of regeneration, where matter is reborn to create the next generation of stars and planets. In its final moments, C.W. Leonis remains a source of inspiration and a powerful testament to the complexity and grandeur of the cosmos. C.W. Leonis as a resource provider. Although C.W. Leonis, or IRC plus 10,216, poses a danger to nearby planets through intense radiation and massive material ejections, its role in the universe extends beyond destruction. For planets farther away in the stellar system or neighboring regions of space, C.W. Leonis becomes a valuable resource provider, contributing significantly to planetary formation and the potential for supporting life in the future. Throughout its life cycle, C.W. Leonis ejects large quantities of dust and gas rich in carbon, oxygen, and complex chemical compounds. These elements not only enrich the interstellar medium, but also serve as essential building materials for the formation of new celestial bodies. As these clouds of dust and gas spread across space, they can combine with other gas clouds to form massive nebulae, cradles for the next generation of stars and planets. This demonstrates that the death of a carbon star like C.W. Leonis is not an end, but a vital part of the cosmic matter cycle. The tiny dust particles emitted by C.W. Leonis, carrying elements like carbon and oxygen, are not only fundamental components of inorganic materials, but also precursors to the formation of organic molecules. Carbon, an essential element for life, has the capacity to form complex molecular structures such as amino acids or hydrocarbons, key ingredients in prebiotic chemical reactions. When these elements reach distant planets or blend into nebulae, they create an environment rich in potential for chemical reactions, leading to the formation of organic molecules, the foundation for life. Planets situated farther from C.W. Leonis hold a distinct advantage in leveraging this resource. While planets closer to the star face destructive radiation and the risk of annihilation, those farther away avoid direct impacts from the star's radiation and gravitational forces. Instead, they benefit from the influx of carbon-rich material and other heavy elements, fostering atmospheric development or geological transformations. If conditions are favorable, these planets could become life-supporting worlds, or even the starting point for future biological evolution. C.W. Leonis's role as a cosmic material generator underscores the significance of carbon stars in recycling and sustaining the cosmic matter cycle. The carbon-rich dust clouds not only supply materials for new stellar systems, but also play a crucial role in shaping the characteristics of celestial bodies. The existence of nebulae formed from C.W. Leonis's ejected material is clear evidence of the universe's ability to recycle matter from the death of one star to create new worlds. Moreover, infrared observations from telescopes such as Spitzer and James Webb have provided detailed insights into the chemical composition of these dust clouds. The collected data not only enhances our understanding of C.W. Leonis's role, but also opens opportunities for studying the formation of organic molecules in interstellar environments. This lays the groundwork for further research into the chemical evolution of the universe and highlights the role of carbon stars in shaping conditions for life. C.W. Leonis, even in its final stages, is not just a dying star, but also a provider of invaluable resources for the cosmos. The elements and compounds it ejects contribute not only to planetary formation, but also to the vast potential for life to emerge in new stellar systems. This underscores that the death of a star is not merely an end, but also the beginning of a new cycle, where material from a carbon star can lay the groundwork for life in the future. In conclusion, CW Leonis is a vivid testament to how carbon stars contribute to the universe's evolution. From enriching the interstellar medium with essential elements to supporting life on distant planets, CW Leonis demonstrates that even in a star's collapse, the universe continues to create new opportunities for life and growth. The death of CW Leonis is not the end, but a new chapter in the infinite story of the cosmos.